Building piling can be used for a practical earthing grounding system, offering several benefits including cost savings on earth mat installation and materials, and utilization of existing building infrastructure. There are some requirements for the building piling. Firstly, the building piling must meet electrical conductivity and structural integrity standards. Secondly, the piling must be interconnected with a continuous conductor. Thirdly, additional measures may be required to enhance electrical contact between piling and ground. Several methods can be used to connect the piling to the grounding system. 1. Direct connection. Connect a bare copper conductor directly to the top of the piling at the base of the building and extend the conductor to the main grounding busbar or earth rod. 2. Exothermic welding. Exothermic welding creates a permanent molecularly bonded connection between the conductor and piling. Weld the conductor to the exposed steel reinforcement bars within the piling. 3. Clamping. Use suitable clamps to secure the conductor to the piling and ensure good electrical contact by cleaning the piling surface and using anti-corrosion compound. 4. Soil enhancement. In areas with poor soil conductivity, add conductive material such as bentonite or graphite around the piling to improve the electrical path to ground. After installation, it is important to verify the effectiveness of the earthing system. Perform ground resistance testing to ensure that the earthing system meets the required values and monitor the earthing system regularly to identify any issues or changes in resistance. For further information, refer to these references. IEEE Standard 80-2013 Guide for Safety in Alternating Current Substation Grounding, International Electrotechnical Commission, IEC 62000, 305-3 Protection Against Lightning, Part 3 Physical Damage to Structures and Life Hazard, and National Electrical Code, NEC Article 250 Grounding and Bonding. Commercial projects where building piling systems have been successfully used for grounding include Marina Bay Sands in Singapore, Burj Khalifa in Dubai, and One World Trade Center in New York City. Additional considerations include ensuring coordination with structural engineers to verify the structural integrity of the piling system, considering potential electromagnetic interference, EMI issues caused by grounding through building piling, and obtaining approvals from local authorities and utility companies before implementing the system. When implementing a grounding system using building pilings, several key aspects must be meticulously addressed to ensure safety, effectiveness, and compliance with relevant standards and regulations. These aspects encompass material selection, connection techniques, soil conditions, testing protocols, and ongoing maintenance procedures. The choice of materials for conductors and connections is paramount in establishing a reliable grounding system. Copper conductors are generally preferred due to their excellent conductivity and corrosion resistance. The size of the conductor must be adequately determined based on the anticipated fault current to ensure it can safely carry the current without overheating or failing. The connections between the conductor and the building pilings must be robust and durable to maintain a low resistance path to ground over the lifespan of the structure. The methods used to connect the grounding conductor to the building pilings significantly impact the overall effectiveness of the grounding system. Direct connection involves physically attaching the conductor to the piling using methods such as welding or bolting. Welding, particularly exothermic welding, creates a permanent molecular bond between the conductor and the piling, minimizing the risk of corrosion and ensuring a low-resistance connection. Bolting, on the other hand, requires careful selection of hardware and proper torque to maintain a secure connection over time. Clamping is another method that utilizes specialized clamps designed to grip the piling and the conductor tightly. These clamps must be made of corrosion-resistant materials and installed according to the manufacturer's instructions to ensure a reliable connection. Soil conditions surrounding the building pilings play a critical role in determining the effectiveness of the grounding system. Soil resistivity, which measures the resistance of the soil to electrical current, varies depending on factors such as moisture content, mineral composition, and temperature. In areas with high soil resistivity, additional measures may be necessary to improve the electrical conductivity of the soil. Soil enhancement techniques involve adding conductive materials such as bentonite or graphite to the soil around the pilings. These materials help to reduce the soil resistivity and improve the flow of current to ground. Proper compaction and moisture control are also essential to maintain the effectiveness of the soil enhancement. Regular testing is crucial to verify the performance of the grounding system and identify any potential issues. Ground resistance testing measures the overall resistance of the grounding system to ensure it meets the required values specified in relevant standards and regulations. The follow of potential method is a common technique used for ground resistance testing, which involves injecting a test current into the ground and measuring the voltage drop to calculate the resistance. Periodic inspections should also be conducted to visually assess the condition of the conductors, connections, and grounding electrodes. Any signs of corrosion, damage, or loose connections should be promptly addressed to maintain the integrity of the grounding system. Ongoing maintenance is essential to ensure the long-term reliability of the grounding system. This includes regular cleaning of connections to remove dirt and corrosion, tightening of bolts and clamps to maintain secure connections, and retesting of ground resistance to verify continued performance. In areas with harsh environmental conditions, such as coastal regions or industrial sites, more frequent maintenance may be required to prevent premature degradation of the grounding system. It is also important to keep accurate records of all inspections, tests, and maintenance activities to track the performance of the grounding system over time. Adherence to relevant standards and regulations is paramount in ensuring the safety and effectiveness of the grounding system. The National Electrical Code, NEC Article 250, provides comprehensive requirements for grounding and bonding electrical systems in buildings. These requirements cover aspects such as conductor sizing, grounding electrode systems, and bonding of metallic components. IEEE Standard 80 provides guidance on safety in alternating current substation grounding, including methods for calculating ground resistance and designing grounding systems. IEC 62305 provides requirements for protection against lightning, including the design and installation of lightning protection systems. Coordination with structural engineers is essential to ensure the structural integrity of the building pilings when used for grounding. The attachment of grounding conductors and connections to the pilings must be carefully designed to avoid compromising the structural strength of the pilings. Structural engineers can provide guidance on the appropriate methods for attaching grounding components and ensure that the pilings can withstand the additional stresses imposed by the grounding system. Consideration of potential electromagnetic interference, EMI issues, is also important when grounding through building pilings. Grounding systems can act as antennas, radiating electromagnetic energy that can interfere with sensitive electronic equipment. To mitigate EMI, it may be necessary to install filters or shielding to block unwanted electromagnetic signals. Proper grounding techniques, such as single-point grounding, can also help to minimize EMI. Obtaining approvals from local authorities and utility companies is typically required before implementing a grounding system using building pilings. These approvals ensure that the grounding system meets all applicable codes and regulations and that it will not interfere with the operation of the electrical grid. The approval process may involve submitting detailed plans and specifications for the grounding system and undergoing inspections to verify compliance. In addition to these technical considerations, it is also important to address safety concerns when working with grounding systems. Electrical workers should be properly trained in safe work practices and equipped with appropriate personal protective equipment (PPE). Grounding systems should be de-energized before any work is performed on them to prevent electrical shock hazards. Warning signs should be posted in areas where grounding systems are present to alert workers to potential hazards. Furthermore, the design and implementation of a grounding system utilizing building pilings necessitates a thorough understanding of soil composition and its impact on electrical conductivity. Soil resistivity, measured in ohms meter or ohms centimeter, is a critical parameter that determines how well the soil conducts electricity. Factors influencing soil resistivity include moisture content, temperature, salt concentration, and particle size. Sandy soils, for instance, typically exhibit higher resistivity compared to clay soils due to their low water holding capacity and larger particle size. To accurately assess soil resistivity, geotechnical surveys and soil testing should be conducted at the site. These tests involve injecting current into the soil and measuring the resulting voltage drop to determine the soil's resistance to electrical flow. The data obtained from these surveys is then used to design a grounding system that effectively dissipates fault currents into the earth. Moreover, the depth at which the building pilings are embedded in the soil significantly affects the grounding system's performance. Deeper pilings generally provide lower ground resistance due to the increased contact area with the surrounding soil. However, the cost and complexity of installing deeper pilings must be weighed against the benefits of reduced ground resistance. In some cases, it may be more cost-effective to use multiple shallow pilings connected in parallel to achieve the desired ground resistance. The spacing between pilings also plays a role in the overall effectiveness of the grounding system. Closely spaced pilings tend to have overlapping zones of influence, which can reduce the overall ground resistance. However, excessively close spacing can also lead to increased installation costs and potential interference with other underground utilities. Therefore, the optimal spacing between pilings should be determined based on a careful analysis of soil conditions, piling dimensions, and project constraints. Furthermore, the choice of connection method between the grounding conductor and the building pilings is crucial for ensuring a reliable and long-lasting grounding system. Exothermic welding, as previously mentioned, offers superior performance compared to mechanical connections such as bolting or clamping due to its ability to create a molecular bond between the conductor and the piling. This bond eliminates the risk of corrosion and loosening over time, ensuring a consistent low-resistance connection. However, exothermic welding requires specialized equipment and trained personnel, which can increase installation costs. Mechanical connections, on the other hand, are easier to install and maintain but may be more susceptible to corrosion and loosening. To mitigate these risks, it is essential to use corrosion-resistant hardware and to periodically inspect and tighten the connections. The size and type of grounding conductor used in the system also play a critical role in its overall performance. The conductor must be sized appropriately to handle the anticipated fault currents without overheating or melting. Copper conductors are generally preferred due to their excellent conductivity and corrosion resistance, but aluminum conductors may also be used in certain applications. The conductor should be protected from mechanical damage and corrosion by using appropriate conduit or direct burial techniques. Additionally, the grounding system should be designed to minimize the risk of step and touch potentials, which can pose a safety hazard to personnel in the vicinity of the grounded structure. Step potential is the voltage difference between 2 points on the ground surface that a person could contact with their feet. Touch potential is the voltage difference between a grounded structure and the point on the ground that a person could touch simultaneously. To mitigate these hazards, the grounding system should be designed to distribute fault currents evenly throughout the ground and to minimize the voltage gradients near grounded structures. This can be achieved by using a grid of interconnected grounding conductors and by installing ground mats around equipment enclosures. Proper signage and training should also be provided to warn personnel of the potential hazards associated with step and touch potentials. Furthermore, the grounding system should be coordinated with other electrical protection devices, such as circuit breakers and fuses, to ensure that fault currents are cleared quickly and safely. The grounding system should be designed to provide a low impedance path for fault currents to flow back to the source, allowing the protection devices to operate effectively. Coordination studies should be conducted to verify that the protection devices are properly sized and coordinated to provide adequate protection for the electrical system. In addition to the technical aspects of grounding system design, it is also important to consider the environmental impact of the system. The use of certain grounding materials, such as copper, can have a significant environmental footprint due to the energy and resources required to extract and process these materials. Therefore, it is important to consider using recycled or sustainable materials whenever possible. The disposal of old grounding materials should also be done in an environmentally responsible manner to prevent pollution of the soil and water. Furthermore, the grounding system should be designed to minimize the risk of stray currents, which can cause corrosion of underground pipelines and other metallic structures. Stray currents are electrical currents that flow through the ground due to imbalances in the electrical system. These currents can cause accelerated corrosion of buried metallic structures, leading to leaks and failures. To mitigate the risk of stray currents, the grounding system should be designed to minimize the potential for current leakage into the ground. This can be achieved by using insulated conductors, minimizing the number of ground connections, and implementing cathodic protection measures. Regular monitoring of the grounding system should also be conducted to detect any signs of stray currents. Finally, it is important to document all aspects of the grounding system design, installation, and maintenance. This documentation should include detailed drawings, specifications, test results, and maintenance records. The documentation should be kept in a safe and accessible location and should be updated regularly to reflect any changes to the system. Proper documentation is essential for ensuring the long-term reliability and safety of the grounding system. In summary, designing and implementing a grounding system utilizing built-in pilings requires a comprehensive understanding of soil conditions, connection methods, grounding conductors, electrical protection devices, environmental considerations, and documentation practices. By carefully addressing these factors, it is possible to create a safe, reliable, and sustainable grounding system that protects personnel and equipment from electrical hazards. Regular inspections, testing, and maintenance are essential for ensuring the long-term performance of the grounding system.